Yeah, okay, fine. So the topic is very relevant. In fact, no, nowadays when we talk about for the high performance computing and the various technologies which are coming up, so I try to align my presentation so that no, it covers multiple of technologies and gives you most idea of how these technologies are emerged. And I also take an opportunity for you to introduce how these technologies of HPC are emerging into a new generation of technologies which is also meant for the autonomous navigation systems, which is also we call like a drones, right? So my presentation will go for mostly for 1.5 hours, and hope that no you can able to understand some of the concepts, and based on that you can, I'll take the questions maybe at the end of the last no the few minutes of the thing. So till the time, let me put up the technologies and how these kind of technologies are emerging into the market. Okay, so I share my presentation so that you can able to see. Okay, to screen. Yeah, I'm hoping my screen is visible, right? So
Yes, sir.
Yes, visible, sir.
good, right? So when I do this kind of the thing, probably I have to shift over one or two presentations where I have to move the things here and there, right? So as I told, it is mostly like the when we talk about the technologies here, as we have been discussing about AI and machine learning and deep learning with HPC frameworks. So if you see this, I'll be covering about most of the frameworks which is being done in the artificial intelligence, machine learning, and in fact the deep learning with various high performance computing technologies and the frameworks, right? So and most of the technologies when you will see now, they have been emerged and converting into the various platforms. So starting from the cloud computing technologies, and after that it came to the edge. Now from the edge again, the people are now talking about an IoT devices, internet of things devices, and again from internet of things devices, now the convergence has been happened towards the autonomous navigation systems, which we call like the drones, unmanned aerial vehicles, then followed by the autonomous navigation systems, which also include about the unmanned aerial vehicles and also the unmanned ground vehicles, which are also called as the robotics, and unmanned water vehicles or surface vehicles, which nowadays these vehicles are also traveling over the sea and also the water. Now most of the things, if you see, always the one thing which makes the great importance of the thing is the computing power. So the computing power, when we talk about the HPC, the high performance computing, so we always, people coming from the background of the computer science, we always think like a power HPC in the sense like having a large system of systems where there is a large of computing power. It could like a distributed systems, or we also talk about something like a cluster computing, and we also talk about a cloud computing, and we also talk about like a previous generations of grid computing, and where we always talk about having a supercomputer, right? So HPC means we always think like a supercomputer, right? But if you see the technologies over a time period, the supercomputers are still being used as the backend computing technologies, where they call like a remote computing layer. Then followed by what we have now, the HPC is being emerging as a new generation technologies. Is now the HPC is also coming on to the smaller edge boards, where the HPC is also performed on the edge computing board, right? So I hope most of you are aware of the edge computing and also the other technologies. But once I get into the slides, I'll cover you where this edge, other technologies are coming into the technologies umbrella. Now, when we talk about the HPC, so just try to, I want to bring you people thinking of HPC is not just for supercomputing power. Now the HPC is moved to the edge, right? So that means now the HPC technology, when you talk about, most of these edge computing devices are also performing the high performance computing, right? So the high performance computing, I hope by this time most of the audience and the participants are aware of the HPC technologies. And so then we'll introduce some of these HPC technologies, and we'll get into the things, how the things will go into the things, right? So uh, my things will go something like this, where we'll be talking about the HPC, high performance computing, then followed by the HPC technologies, and some of the things where how these nowadays the technologies of HPC are mostly getting moved on to the cloud as a backend computing infrastructure. Then the edge computing devices are becoming like a more of computing at the source, right? So wherever the data generation is been happening, and after that the final outputs whichever is required are pushed to the edge, right? So that's how the computing scenarios are getting changed. Now we talk about something called as an IoT, cloud and edge computing technologies, where different frameworks are getting emerged. Then we talk about the applications of the cloud and edge. Then we talk about a new computing paradigm, which is a quantum computing, which is also coming like a new generation of technologies within the HPC. Then followed by we try to give some of the things, and depending on the time permits, I will show you some of the things how these the drones like UAVs and the other systems, autonomous navigation systems, are making care of are trying to use the HPC technologies on the edge, HPC edge, where they're trying to build a different types of the computing paradigms and also the different kinds of an applications using HPC as edge, right? So that's what we will try to see. Now, when we see about the HPC, in fact, so HPC is the ability to perform, as everybody knows, when you see about the computing power, right? So the computing, we say that we'll do some calculations, and this calculation has to be done on the processor, and this processor could able to provide me the better computing things so that I can execute my instructions as many number of as things possible, right? So that means if I want to perform any computation, so to perform that computation, obviously I need to have a better resources, and these resources can come from a CPU, or which is like a central processing unit, where it has a memory, it also has some kind of a control unit and arithmetic logic unit, where you could able to perform the calculations. Now coming to the another processor, which generally called like a co-processors, like GPUs, where they could also able to provide you the more computing power, and your algorithm when it demands the applications like where a single instructions can work on the multiple data, which we call like a SIMD kind of an applications. Then we'll go for a GPU kind of a processors. And when you want to have the MIMD kind of an applications, multiple instructions, multiple data, then we'll try to execute that on the CPU, right? So that means the combination of the algorithm or the application demands, you need to write your application such that your algorithm can able to execute either onto the processor, which is like a CPU or GPU. And when you have a streaming kind of an applications where the data is coming like a stream, and you wanted to have the highly sequential data which is to be processed, then you try to go for the streaming processes like an FPGA kind of a processes, right? So that means whenever we talk about an HPC, always keep in the mind, HPC talks about something where you wanted to perform the calculations on the computer as many as possible, so that the time of the computing will come as minimal as down, right? So that means whenever you do the high calculations, very high speeds, obviously the time taken to compute all of them will come down, so that you'll get a result at faster rate, right? So that means the HPC, whenever we talk about the ability to perform complex calculations at very high speeds. This everybody knows, right? So that means if you want to perform the calculations at very high speed, so what we need, obviously we need the number of operations to perform per second should be increased. That means the flops, like a floating point operations per second, try to increase, or like tops where we call like integer operations you can increase. Obviously when you have a more number of floating point operations, integer operations are much better than the floating point operations, right? That means if you want to have the calculations to be done, so what the technologies needs is the technology to computation problem that are too large for standard computers and would take a long time for solving, right? So that means when you have a problems to be solved and they're very too large for standard computers, have to take a longer time to solve the problem. Now when we talk about the HPC, or even if you talk about the HTC, high throughput computing, right? So what we try to do is in the case of an HPC or in the case of throughput, HPC concentrate more on trying to reduce the time computations for a single instructions, right? And or maybe a single job. And when you talk about a high throughput computing, you give a group of jobs and try to reduce the computational time for a group of jobs rather than working on a single job at the instruction level. So that's how the way the differences comes. So when we talk about achieving this HPC, always we try to see that you cannot look into the system as a standalone, not just like a computer where we buy, where we say that okay, I bought a computer which is working at a clock rate of a 3 gigahertz, having a RAM of maybe so and so, having a better throughput of a RAM, or maybe the performance of an IO of the RAM where I try to get the data, and I also have a better storage, which is like the flash kind of a storage or SSD kind of a storage. And if I say that yeah, yes, I have a good computing resources, but if my algorithm doesn't trained or my algorithm doesn't tuned for using all these resources, we will not get an HPC, right? We will not get it, right? So what has to happen whenever you want to do the HPC? HPC is an engineering paradigm where one has to look all of them into the holistic approach. That means your algorithm, what you are trying to code, should have a parallelism into the nature. And after that, the algorithm which you coded should be able to exploit the underlying computing resources, including the processor, including the processors, and including the memory, and including the disk. All of them should be effectively used. Then only one could able to compute the high performance computing ratio to get into the application. So that you always remember. Most of us will, as a misnomer, thinking that I bought a laptop or the computer or the workstation or the server working at so and so clock speed of, let's say, some X. Now I brought another computer maybe after some time where it has a clock speed of X plus 5, okay, or X plus some incremental thing, and they think that no, the algorithm whatever is written should perform much better on that X plus incremental processor. It never happens, right? It may happen to, it may, you may get some little bit of performance improvement because the clock speed has increased, but it doesn't mean that without changing the algorithm, without having a changes that you're trying to do in the algorithm to exploit the course, you will not get a better performance, right? That's what it goes. If you talk about nowadays in the market, you will see the computer with a number of cores or more, right? You'll see like a dual core, octa core, hex. No, after that you will say that 16 core, a processor having something like a 16 cores, 32 cores, 64 cores, right? That means each core, when you talk about, is a computing element which is available. But however, if your algorithm is not able to multi-threaded, if your algorithm is not able to go for a multiple kind of an applications to execute, then there is no use in getting the number of cores, having that kind of computer, right? So always talk about, always we need to think about something called, whenever I have a computing power, having the more processor, it could be like the node, or even it could be the computing power where I have with the number of cores or computing cores. So I need to also have an algorithm which can actually, exploit all these computing cores which is available, effectively utilizing the disk with an IO better rate, and also for getting the more of the clock which is coming from the RAM itself, right? So that's what we need to think about for the next, for the application that we're going to do. Like for example, simple applications, when you talk about, let's say that I'm writing for something called as a searching application, right? If a searching applications, if I write, there are so many searching algorithms starting from linear search, binary search. Again, you can also go for some kind of an hashing mechanisms, and the binary search also can go with the different types of data structures also, right? You can also go for the array based, you can also go for the tree based, like different mechanisms are available. Now if you talk about a linear search, if you implement, and where you will go sequentially, where your algorithm is not made for to execute in the parallel. Even though if you try to execute the linear search on the system, even on the parallel system, parallel computing, because your code is sequential, your algorithm is sequential, you don't get a better performance, right? So for that, what we try to go, we try to go for a binary search where we try to divide the data into the multiple sets, and the logic is same on the data, so that I can give the each logic to one computing core, so that I'll get a better performance because I have the number of computing cores are more, and my algorithm is also made like a more of parallel, so that I'll get a better results, right? Like for example, let's say that I have data which is coming something like a 1 millions of records, 1 millions of numbers. That means 10 lakhs. Let's say that I have a computing cores of 10. So what I try to do is, for each computing core, I try to give like a 1 lakh of a data, so that what 10 lakhs of a data is given to the 10 computing cores, and each computing core will search and give me the number which I'm trying to see, and all of them will like multiple threads. And these multiple threads, when they work, earlier where it is going to take time of 10, now the time of 10 is coming to the 1x, right? So that means 10 seconds is now coming to the 1x, 1 second, because now they have a, all these things are executed parallelly. Is it right? That's what you will try to go for, the multi-thread programming, or whenever you write right now the number of threads where it can go and exploit the things, right? So that's what it happens when you talk about for the computing cores. Now, when you talk about this desktop or computer workstation, generally has few number of processors, right? On the other hand, HPC has a network of nodes with CPU and accelerator computing devices with its own memory. That's the beauty of it, right? Like when you talk about the example that I gave you for the binary search, yeah, obviously it comes into the a methodology which is called SIMD, right? Single instruction, multiple data. That means, what is my single instruction? The single instruction is the logic which I'm searching for the number, and the data which I'm going to do is a multiple. That means the data of 10 lakhs, that's 1 million data, is getting divided into chunks of 1 lakh of a data, and this becomes like a multiple data. But my logic of instruction execution, or my logic of doing it, is like for searching, which remains same, right? So that means if you talk about a GPU kind of a language, what is being done, like this data is being created into the threads of no, the 10 threads, and these 10 threads are given to the data, where each of them can execute multiply simultaneously on the multiple data, and you get 10 results where, like whichever the number is found, that thread will give you the data which is being searched. then finally you can say that yes, the number is found or not. You could able to tell at the much faster rate, right? This is what happens when you talk about a single system. Now when you talk about HPC, when you extend it for the the more, so you talk about it's not like a single system, you try to make like a systems which is like a cluster, right? More number of systems, we talk about no like a cluster of systems. When you talk about for a cluster of systems, it is not a single. Now there are multiple nodes which are interconnected together, and these interconnected together, you talk about no you know internet, let me see, I have a, okay, so right, so when you talk about like these kind of a systems, when you see there are so many systems which are joined together, and you can see like a backend they're being connected with the, the network, and these networks and having the better IO, then you could able to perform the computations at faster speed, much at must no at much faster speeds, right? So that's what you talk about no the cluster computing, where in the case of a cluster computing, the nodes are kept it like horizontally scalable, and all these nodes are connected towards a network through some kind of a networking computing. And whenever you write a program, you see that the program goes to the multiple nodes and execute and get the results, right? The first one which I told you, the searching, is something called they're all execute on a single system. But if you have multiple jobs, right? So multiple jobs I have, each job is independent. Now I'm getting something called people are submitting a jobs in my office, and people they say that no, somebody is trying to do some kind of a modeling, somebody is trying to do the simulations, somebody is trying to do the AI deep learning applications, and somebody is trying to see that the algorithm functioning on the image processing, and somebody has written a code working on the video processing, and somebody has written a code for a navigation system, right? Like this, I'm getting a multiple jobs coming from each people, no, written for different things. So then the computing power has to be given, right? So then how do we give the computing power for them? So the thing is, you try to make it like a cluster of systems, and the jobs are submitted to that. Each job can understand that know how much of a computing resources are required, and depending on that, it maps to that system, right? That means when you're trying to address it for a single job and trying to multiple, if the job can be divided into multiple things, yes, obviously we can execute on a single system, right? Where the multiple threads can be executed on a single system to do that. Like this, if you have multiple jobs are coming, you try to schedule it to the multiple computer systems where it can able to execute and give the results in the better way, right? That's what we'll use the programming language like OpenMP, MPI, where OpenMP gives the multiple threads which can be executed in parallel. And when you talk about an MPI, message passing interface, where you could able to see that all these jobs are getting executed on the multiple systems, right? So that's what when it comes when you go for the network of nodes and network of the system. And these concepts have been in fact came from something called as cluster computing, right? Cluster computing, where cluster of systems are joined together, and where you could able to perform the computations at much better way, right? So that's how the technologies of a cluster and technologies of the where network computing still remains. However, the various frameworks have been come over these cluster computing technologies to make use of the things in much better way, right? If you see about the HPC nowadays, HPC has been proliferated into the many ways, right? So now the if you talk about now the older generation systems, where people talk about an HPC means they only talk about a cluster of nodes. Like I have a supercomputer. Now also we have a supercomputer, right? I say that I have a supercomputer which can able to perform no the which can has the compute which can able to perform something called no the 100 petaflops of a computing. Okay, so something like 100 peta. That means you could able to perform 100 petaflops means very huge computing, right? So it's like like a giga, mega, giga, then like a peta, no, it's like almost like a 2 power of 50, no, beyond that, where you could able to perform the computation times. So that much of power is available. But how do we get it, the power of the computing? It is not possible from a single system, that one has to always remember. So whenever you talk about a supercomputer, it is not a single system, but it's a group of systems which have been engineered to perform the computations, where you could able to perform that much of a computations of a flops, where multiple jobs can be performed together on multiple systems together. So that's what people try to build the HPC systems, right? Like everybody has nowadays. If you talk about most of the institutions of an R&D, they have the HPC systems, right? Like ISRO has an HPC, DRDO has an HPC, CDAC also an HPC system, right? They use it for the different applications, right? Like for example, if you talk about an ISRO uses HPC for doing the earth observation systems, and also for the navigation systems, and also for the communication systems, right? Similarly, if you talk about the DRDO has the systems where they use it for different types of algorithm development for the navigation systems, and also for some of their internal built-in applications where they submit a job and get the results out of the supercomputer, right? So probably you can ask a question, sir, but why this when we have already the better workstations, better desktop systems, and better kind of a servers, still do we need the HPC systems? Obviously you need, right? The reason is when you want to do the kind of some modeling and applications, the when you submit it to the one node, you could able to address the requirement coming from maybe a couple of persons, maybe like a 2 3 persons like this. But if there are the number of applications or jobs grows, no, like enormously, which goes like, no, I cannot say like an exponentially, but it goes like enormously, maybe like a quadratic kind of a nature. So one system or 10 systems cannot able to do, right? You could able to perform multiple things together, right? Like for example, if you talk about for the thing, for example, take a case study of the data which we are trying to use this kind of a satellite image processing, right? The data which is coming from the onboard, which is coming from the orbit of a satellite which is being placed on the space, and it is continuously taking the data, and this data has to be given for the, no, for the processing onto the ground. So there is a downlink information coming to the communication, and it goes to the ground. On the ground when you want to process, so a single system is not enough. Okay, so you need a multiple systems together. So these multiple systems are interconnected together, and the data once it comes, so depending on the load on which it is available, then the applications are mapped to that, right? That's why it goes for the HPC kind of an applications. Now when we see about these HPC applications and no, the computers, they've been now playing a major role for the artificial intelligence and machine learning, that we need to always keep in mind, right? So earlier technologies are something where we used to talk about doing some algorithm, doing some computation, doing some distributed computing, and doing some kind of, no, remote based computing, other things. Now as the advent of the machine learning and the artificial intelligence like a deep learning and other mechanisms are emerging, now HPC is becoming like very very popular into the thing, right? So okay, now if we talk about an HPC, just to have a overview of the idea, so it is like there are many top 500 list, there are many HPC supercomputers are available, like a supercomputer which is from Japan, US, China, right? So like a 2020 they built, they call like a Fujitsu, which is Fugaku. Then IBM also has, right? So there are many top analysts. There are many supercomputers which are available, which are being used for the computing purposes, right? So if you talk about, the number of nodes, that's what they talk about for the Japanese system. Which this slide is not for you to maybe to get, but to have an idea like the nodes, right? 1,58,976, and this system, if I'm not wrong, they made it with the combination of the CPU and GPU together. That means they use the multiple CPUs, and also they use this the GPUs also, and based on the demand, whether the job demands for the CPU and GPU, sometimes CPU both GPU together, so then it is being scheduled to that node to the computations, right? Like for example, even in our case also we use the CPU GPU together. Like there is a some code, piece of code which cannot be parallelized, right? So I need to do the computation sequentially, so then we'll try to go for logic where it can be parallelized on the CPU. And however, if I want to do the kind of the processing on the images like a block based processing, so then the GPU is good for doing it, right? Like for example, let's say I wanted to first understand I want to go that understand and see that how much of the total the the image which I'm trying to get, right? Like after that I wanted to do the block processing, right? So in that case what we need to do, there's some text information has to be extracted, where we need to understand, get the information which I'm going to get from the text file, and after that the metadata information. Essentially after the metadata information which I got, so I cannot do this metadata extraction on the GPU, so we can do it on a CPU. So once I have an image, on this image I can able to perform the block processing. So whenever I want to go for a block processing, we'll go for a GPU to be selected, right? So that's how the things will go like together. So if you see about the supercomputers, where they in fact the give much power to do that, right? Like one of the, if you talk about how these supercomputers are built is, like we have a first layer which goes like a cache, second layer is the based on the file system, and the third layer which goes like the storage services which to do the processing, and they're all based on the different types of architectures and framework like an MPI, OpenMP, Tark, PBS, OpenPBS, right? So there are so many things which comes into the to do that kind of a work. Now later to that, if we talk about the HPC, especially what that comes is, one is the multi-cores, then followed by the high-speed clock, then the memory, which is a high-speed memory, then followed by the storage, which is high-speed storage, then the network, which comes like high speed of the the data transfers, then the bandwidth, how much of is been we are getting. Nowadays, we talk about it, bandwidth like 1G, 10G, right? Then it goes like 40G, then 100G, 200G, right? So that's a bandwidth that you can able to perform over a network of transfers, right? Then the accelerators are available like a CPU, GPU, like CPU is not an accelerator, in fact, it's like a main computing, GPU, FPGA, and now the processors are also coming like quantum processors, right? So that means quantum is also now getting emerged as another HPC technologies where these quantum processors are good for performing the probability based computations, right? Like CPUs, and if you talk about CPU, they're very good for deterministic computing where you know that answer to be done. But if there is a probability based computing, then the quantum processors are very good processors where you want to do the probability based computations, where the data of the bits will get represented into a different form, and this different form will able to perform you the probability based computations, right? So we'll see how these quantum processes are also used in the HPC technologies, right? Now if we see about the HPC realizations, like different types of frameworks and do that, one is the cluster computing, as everybody aware. So group of nodes connected to achieve distributed and parallel processing with computing, where it was a in fact older technologies, but it has given a birth to many of the technologies, right? So it is like solve the large complex intensive problems into the the various administrative domains, right? So like grid computing was mostly used for the R&D and the mostly for academic purposes, where a large computing clusters are joined together, and each large computing cluster becomes like the cluster, and these clusters are joined together as one administrative domain, and this used to call like a grid, and people used to submit a job to the grid, and the backend grid used to identify this job has to go to which cluster, and based on that the applications used to run, then the results used to get back, right? So grid computing in fact was popularly made by CDAC in the India. Then they call like a Garuda grid they made. After that they moved to the cloud. They call like a Meghdut, right? So much of technologies and variations have come when these things have been built over a time period, right? Later to that, the other technologies also came with HPC, which is called as a cloud computing, right? So cloud computing, in fact, when we used to talk about the cloud computing a few years ago, we need to teach about cloud computing starting from this architecture to how the realizations happens with the different types of the layers like infrastructures, platform, then the service layers, right? Now people are not aware of cloud computing very much, right? So people nobody's now talking about IaaS layer, PaaS layer, SaaS layers. Those technologies have been gone. Now, when we see about the cloud, yeah, obviously the cloud has given a birth to the many technologies as well, right? So, and even though it has taken its features from the cluster and grid, but in fact it has overtaken the most of the things, and the cloud has become very very popular now. Now, most of the applications when you talk about for an HPC, either starting from the Amazon Web Services, which has been given as a cloud, or even it could be the Windows, which has been given as a services over an Azure platform, or even it could be the many data centers which are also giving like a cloud-based platform, where the services are being given, the computing, storage, and other services has been served as a services over the cloud networks, right? So that's how the cloud has become a very popular technology, and it's become like on-demand pay-as-go computing model to solve large complex the problems where people can rent the services, and they could able to rent the resources, and they can able to compute and get the results out of it, right? And nowadays cloud computing has become like a back-end computing infrastructure, for most of the applications to do that, starting from handheld devices to the even to the services that we use on the laptop, or even the desktops, or even the workstations, or even on the servers also. They're connected to the backend as a cloud, and they push most of their applications to the cloud, right? So that's how it's become very popular as a pay-as-go computing model. And not only that, is a public clouds obviously pay-as-go computing model, and even the private clouds and hybrid clouds also came. So people know the many organizations are introducing their own private cloud, which is also called as they also call like the private clouds are customized cloud, or they also call it is like the cloud which is meant for the specific purpose, right? So customized cloud, and they try to use it for their the purposes, right? So we used one word called the private cloud, and the other one is the specific to the application specific clouds, right? So that's how the technologies have been emerged for the cloud computing. Now, coming to the cloud, as it has become like the computing infrastructure, and many of the applications are kept. Now, cloud follows a different types of architectures, as everybody aware, where your platform is getting virtualized using the computing layer, which is called infrastructure as a service. Then the applications are developed using a service layer, which is called the platform as a service, and this and the then the then followed by the services has been built making use of the platform as a service as a model which executes on the infrastructure layer, right? So later to that, again the other technologies also came, virtual machines have come. Virtual machines has given a birth to many of the technologies. Then later again, the application virtualization also came, which we call generally like a containers, right? So now the containers are also popularly used for most of the applications nowadays. People talk about for going for a containerization, where these containers will like application virtualization, where each application works its own isolated environment, so that the other environment will not get disturbed, right? And these containers can execute either on a virtual machine, or it can also execute on the physical system, right? So that's how the containers become as popular. And the best people, they use the word called like a Dockers, right? The Dockers has given a Docker sees the technology of the containers, where the containers are being put it onto the system, and based on the demand, you can pull out the container if it's like a, from the public registry, or you can maintain your own containers in the private registry manual way, and you can able to instantiate and submit your jobs to that, right? So that's where the things are now becoming more popular to do that. And again, on top of it, architectures like a microservices have come, where microservices and containers has more or less like no the interrelated together, where the each application you want to build, you build it like a microservice, so that you can have your own applications running within the microservice platform, so that they can execute on the multiple systems and do that, right? Again, to manage the containers, there is another technologies also came, which is like a Kubernetes, where the Kubernetes becomes like a more of an orchestration platform, where the Kubernetes runs for the jobs you can submit, and the backend there is a containers where you can instantiate containers which you would like to execute, and based on that you could able to do the problem doing it, right? All these things as a part of the HPC realizations, but the technologies which have been moved from one platform to another platform to give a birth to many other technologies to do that, right? If you talk about nowadays for HPC, especially for AI and machine learning, the containers, the microservices, that are the Dockers, microservices, Kubernetes, or on top of the Kubernetes, whichever is felt, and all these things are getting executed either on the cloud platforms or in the data centric platforms to realize most of the applications, right? Like for example, if we talk about a Kubernetes kind of a thing, let's say that I have a models which are made. I made one model which executes for the person detection. I made one model which is running for the detecting the cloud, and I made one model which is detecting for the kind of the some models where I'm trying to track the persons, or I wanted to identify the objects, or I wanted to identify the kind of the movements which have been happening, or I wanted to identify the faces, or I wanted to detect the gesture do I want to do, or I want to do some kind of a sentiment analysis. Like this, you have so many things, right? So each model that you create can be made like a containers, and you can put it into the your infrastructure, and this infrastructure can be a cluster infrastructure which is running as either could be a cloud based infrastructure, or it could be running on your local data center itself. Then on top of it, you try to put the containers and put your applications, everything loaded, bundle them, encapsulate all the applications, libraries, runtimes which is required, put also the model weight files into that. Now you try to execute it as you require. Like this, you can run the multiple models working, multiple models running together on the cluster of systems together, right? That's how the HPC has been realized now, right? So that means this is the best example of who somebody is trying to do the learning of these machine learning and deep learning applications, which are made for different purposes, right? For example, one of the best case examples which I tell you, like one of the data once we get from the satellite imagery, and this satellite data may have different types of objects, right? Like it may have a road, it may have water body, it also may have a cloud, it also have the kind of the some built up areas like a building, it also has some kind of the maybe the farmland, right? It also has the vehicles which are moving, right? So these things, if I wanted to see, understand on the data different types of objects which are available, where I wanted to get each of them and do this kind of the inference on these things, right? So wherever the water bodies are there, I wanted to see that water bodies are available, so and so place this number of water bodies are identified, and this number of vehicles are available, or I wanted to track this vehicle, or I wanted to find out no there is a road on this, or I wanted to find out there is some kind of activities are going on, right? So you can have a model, and when the data comes, you can submit it to the backend containers. Containers runs in the cluster mode, and you can get the results. And so that you can able to perform the HPC, high performance computing on the resources, right? So that's where actual parallelism comes into the market, right? And the advantage when you talk about is like the models as the changes and the frameworks changes, runtime libraries changes, and putting on one system and giving a clash for most of the libraries becomes a very, very hectic job, right? That means as these technologies are growing, and managing the kind of runtime libraries, and managing the systems, and managing the libraries, and managing the models, managing the applications, managing the frameworks, managing the programs, managing your code, managing the versions, all those things are becoming very, very problematic, right? So that's what people are talking about when you see about now we talk about nowadays for something called as No, I wanted to go for the DevOps, right? People talk about the DevOps. What is the DevOps? So DevOps talks about your operations. You wanted to make your development operations easier scenario for that, so that multiple people can together, and you can also do the version control management. You can also handle the projects easily, right? That's what they call like a CI/CD, continuous integration, continuous development, right? So that you can develop, you can continuously, develop and integrate it, and so that you can also execute it, right? So people try to use the GitHub, GitLab, then followed by the some backend kind of containers to push your data code into that and try to create a containers and execute it, right? That's where the HPC technologies comes into the picture, right? So that's what I wanted to clear for you. The HPC is something, it is not that what we talk about in the olden days, where I wanted to see a supercomputer we're running it. Yeah, that's obviously is going to be a backend, the supercomputer or the cloud, which becomes like a backend computing infrastructure. But however, the new technologies are arrived now, seeing starting from the microservices architecture, having a containers, having application virtualizations, having the models which are designed, running on the system, and being managed by the orchestration platforms like a Kubernetes, where you could able to get a better, the platform and the computing power from that, right? That's where it comes into the thing. Now, when you also see the HPC realizations, and there is another technologies which have been emerging and doing it, which is called an IoT and edge computing, right? So the IoT and edge computing, when you talk about, which call like an Internet of Things, where most of the devices when they have been connected, and these devices becomes like are all objects which have been connected together into this, right? So that means Internet of Things, when you talk about, there are the devices which have been connected, and they have been connected to network, and this network of devices becomes like Internet of Things, where the data is generated and this data has been moved. Okay, so when we see about the another technologies of HPC edge computing, when you talk about, where the processing happens on the edge, right? So the edge in the sense like in a source, wherever the data is generated at the source, the information processing happens at the edge, and wherever you can able to do the kind of an inference rather than pushing the entire data to the cloud or the remote computing layer. Okay, so that's an advantage when you talk about go for edge computing. Now, when we see about the edge computing nowadays, the edge computing devices are also coming with so much of the power of an HPC, right? Now, if you, for example, if we talk about edge computing devices, where you can have the boards of a GPU boards which are coming, right? So the GPU boards and comes like a system on chip, a system on a module, where these boards sits as a small form factor where it can be handheld devices, where it can be carried on the held like a portable devices, where having the low power consumptions but high computing power which is given, right? So that's where the advantage of HPC edge computing when you go. So if information processing is located close to the edge to reduce the latency in processing in real time, that is close to the edge means close to the source, and real-time computing powers for sensor, video processing analytics, self-driving cars, artificial autonomous systems, and robotics. And these edge computing devices are becoming very, very popular. Okay. So when you talk about the many applications, in fact, for the HPC application, when you talk about, there's an Earth observation system which is being used for environment modeling, like a simulation of earthquakes, weather patterns, climate change, remote sensing. And there are some other applications like a CFD analysis and simulation software. And there are many other applications which have been used for something called the remote sensing and satellite data analysis, and the computational fluid dynamics like a CFD analysis and simulation software, where there's the ability to analyze the complex problems and solving the many of the CFD problems. Like CFD problems, when you talk about, mostly for the structural analysis and the dynamic analysis being used. Like one of the best example to understand about the CFD analysis is, you can talk about if you want to do the modeling of any structure. Maybe let's say that there is a people, you could have seen, whenever there is a satellite launch happens, there is a something called launch vehicle, right? The launch vehicle having a different types of stages when it goes. So it starts from the stage 1, stage 2, stage 3, stage 4, right? Stage 1 we call like strap on motors, then we have a liquid state, solid state, again followed by the again of the another liquid state which goes, right? But each of them, when you want to do, all of them are made with the structures, right? So each one structure, and the structure is filled with the kind of the fuel, propellant. The propellant either could be like a solid, it could be like liquid, and but these propellants which are being filled up, they need to be analyzed how the structure behaves, and the structure how it behaves, how it is trying to move when it is when it is moving, what kind of effects, environment effects may come, right? It could be like there is a pressure which is coming from the air, and there could be the friction which is coming when it is moving, and there is a lot of friction even generated by the thrusters, right? We wanted to analyze and see, is there any the kind of the structure behavior or any kind of anomaly which is going to do. Like most of the times you could have also seen when there is a launch, even sometimes they say that no launch has been stopped for for halted for some time because of some glitches we call. It could be the glitches which are coming from different parts of the things, right? It could be from the satellite, or it could be from the launch. So these kind of things are being, when you do the CFD analysis and understand, you will get to know that yeah, exactly where is the problem, right? So that's what we generally call it, is like the finite element analysis, FEA, where we do the finite element analysis. And do this finite element analysis on the things, you need a large computing power. That's what we're calling ISRO. It also has a supercomputing facility where this finite element analysis of the CFDs has been done on the supercomputing facilities like HPC facilities, where the structures are given, and the structures, different types of elements are given, which is like a finite element analysis has to be done, minute level analysis has to be done, and the models are submitted, especially the structure analysis models are submitted, algorithms are written, and these algorithms runs on enormous number of jobs, as the things on the enormous number of systems, and they give a result how the performance will be there during the simulation time, right? So obviously when the simulation things works much better, and it is closer to the reality, there could be small deviation in that, but however it's very closer to the realities, right? So that means for any kind of a simulation problem, including aerodynamics, thermodynamics, hydrodynamics, and most of these things, especially to understand about the lift and drag field properties as the pressure and velocity is obtained, the supercomputing facility is very much required, right? So, and people think like CFD analysis and HPC means is a not part of computer science. In fact, is a part of computer science. However, these kind of a problems of aerodynamics related will come from the people of aerospace engineering and mechanical engineering, but the code which is written by the things are from the computer science background people, right? So they write the code, and the algorithm is given by them, right? The coding with a better optimization is being done by the computer science people. Okay, just to give a glance of what the CFD analysis is this, because CFD analysis simulation we can talk for many number of hours, but I don't want to get into that much of breadth and the length of that. Now there is other applications, people coming from biochemistry and chemistry, where healthcare and physics also the many studies have been done where these HPC applications has been used, right? So now getting into the frameworks, now HPC as the distributed computing as already told, where we have a cluster, right? So cluster will talk about like a PBS, like a portable batch, the scheduler, or open PBS, or TAR, MPI, right? So I think most of you may be aware of the MPI. MPI and OpenMP both are different. Don't get confused. OpenMP is meant for the multiple programming, where you can write your applications like multi-threaded applications is being provided by the OpenMP, and with multiple cores. It's like more of thread kind of a programming is what OpenMP talks about. But MPI talks about more of a task kind of programming, right? It's a message passing interfaces. Like you have a two tasks. Across the task, you wanted to transmit your data as messages, then it becomes like an MPI, right? So MPI is being works in the cluster mode, and OpenMP runs mostly on the server having multiple number of cores. So that's a difference you need to understand. Now coming to the GPU, where it's mostly used for the accelerated computing, where a lot of the data parallelization is possible, right? So whenever there is a data parallel applications, then we'll go for a GPU, which is mentally meant for the SIMD applications, and where multiple computing cores are available. But writing a GPU programming is an art. Okay, one has to remember it is not so easy. Yeah, obviously now there is a many frameworks have come up like a Torch, PyTorch, many Python libraries also came where you write it internally, they'll take care of doing it, right? But we used to do the programming when this GPU the programming of Python was not available, and even the C code was not available, or C++ code was not available, especially like a framework for GPU, we used to write a code on our own, right? So we used to optimize and write it. So that's the beauty of the writing a GPU programmer, a GPU, the architect when they write, right? So we need to write understanding about the blocks, understanding about the cores, understanding about how do you copy the data from your CPU to the GPU device, and internally how do you write a program to execute on each of the computing cores, and how much time you can able to estimate and do the kind of the optimization for doing it, right? That's what the GPGPU used to go for. It's a very art of programming, GPGPU. Obviously, one used to love writing the GPGPU programming using the CUDA or the OpenCL programming, right? OpenCL was the another programming which is open source. Later, the NVIDIA came up with its own programming architecture called the CUDA. Okay, so the full form I am not remembering, but CUDA became like a very popular programming. Now CUDA has come up with so many libraries now to run on the GPU, right? So you can directly use them like one of the things like a PyTorch. Torch is an example for this, right? So you can directly use the libraries where all these optimizations have been taken care. Internally, you need not to copy the data from CPU to GPU and need not to write an algorithm to do that. Already the libraries are come up to do the multiple computing cores, the executions on that. Yeah, another HPC platform, as I told you, like a semiconductor based devices, which is like a configurable blocks and connected via program interconnect using the FPGA, which is called a field programmable gate array, right? So I hope computer science people, except those who have done some course on embedded systems or maybe some course on the VLSI, you may not have got an opportunity to do the FPGA programming, right? So like HDL, hardware description language, which is also called like a VHDL, very very large scale hardware description VHP. Exactly, I'm not remembering getting the name. Like hardware description language we call, and the VHDL, which is also like a hard, which is in fact part of an HDL. And VHDL is the language. And similarly, there is one more language called the Verilog, right? Verilog comes like a little bit of higher, but VHDL comes like a little bit of lower kind of a language where you need to do a lot of circuits on your own. But in the case of Verilog, it is very easy to do, the programming kind of thing, right? So that's where. But FPGA is meant for the most of the things where the logic, if you can able to reconfigure and do it for the kind of the streaming kind of an applications, we'll try to go from FPGA. Like for example, streaming means, I'll just give a small example for understanding purpose. Let's say that I wanted to do this kind of a the search for some kind of a pattern in my data, right? So the pattern is, I want to do this kind of a pattern searching in terms of a bit, not as a byte, right? Like I have something like I'm getting a data and this data is getting converted into bits. Like I'm getting some data continuously, right? Some data I'm getting, and this data I need to convert into the bit, and I wanted to search for a pattern which is for a bit level matching, right? I don't want to do that byte level, but I want to do bit level matching, right? I want to do the byte level matching, or I want to search within a byte particular kind of, the bits where I wanted to do, right? So like if you want to do that kind of applications, right, then FPGA is much better for doing it, right? And also it is also good for the serial based computing where you wanted to do the serial computing but highly parallel, right? Sequential computing and highly parallel. That's the way you go for an FPGA kind of programming, right? Once you are an HPC expert, being an HPC engineer or HPC expert, one should know about all these technologies and the programming frameworks and the models. Then you could able to appreciate and love the HPC, the technologies for to do that, right? That's where you need to develop the mechanisms of understanding and loving those kind of programmings for getting all these kind of languages, and also for getting your hands wet, the to get into those things. But people obviously love the FPGA programming nowadays for especially for edge computing devices where I wanted to process something called 2000 frames per second. My camera rate is 2000 frames per second, where I wanted to process this as the data coming from 2000 frames. Each frame I wanted to process within 1 second of a data, I'm getting ready for the another 2000 frames per second to process, right? Like for example, if we talk about most of these deep learning applications where I wanted to do this kind of a tracking of an object, and this object is moving very fast, right? So then in that case, people try to use these kind of FPGA devices because they're very good to operate at very very high data rate, and each one goes like a sequential where you could able to put your data and do that. And also the most of these kind of the signal processing things are being done in FPGA, right? So people, those who are trying to address on the signal processing and signal communications, and people trying to work on the video kind of a processing using the things, FPGAs are becoming very very popular, right? So that's how you need to develop the technologies, right? So now let's say that once we have this HPC, and as I already explained you, the cloud computing, where it has become like a back-end computing technology, so people are aware of it already. So I need not to discuss about much on the the things. Like one thing which you have to see, like now the community clouds also came, where trying to address our own cloud for that. Like we also have our own cloud where we set up for our own purposes, where we are trying to run this kind of a containers, microservices, architectures, and deep learning models, where people submit jobs, and we'll try to give them the platform where they can able to do the CI/CD integrations and putting the models and running their models onto the based on the community cloud infrastructure, or we call it a private cloud infrastructure, which is not given to the outside people to access it, right? So that's where the HPC comes into the as a the backend high computing facility for one to use for this, right? So the technologies behind everybody knows for the cloud. One is the virtualizations, and which has given like the birth to the various virtual machines where you can create. Then after that, the virtualization becomes like the virtual machine becomes like a thick and heavy, and that's where the containerization will come, like a dockers, where you can run these dockers or containers on the virtual machine or the physical system, so that multiple instances can be run, and each one is encapsulated with its own environment, and without hampering the other without hampering the other environments, right? Each application runs as a containerization within their own isolated environment, not hampering to the other applications which have been running, right? So the consolidation of the resources becomes much more better to do that, right? There is a many public clouds available, right? Amazon and other things, where the Amazon also provides HPC facility on their own cloud, right? You can able to say that, no, I want having HPC facility of a CPU, GPU, and having these things which are connected, and I wanted to put my things and do that. It's possible, right? But it depends on your requirement. So people also will ask, like, for us, they say that, no, why are you trying to set up? You can take it from the Amazon itself for the resources. But obviously, one is the, you need to pay the things, right? But at the same time, if you wanted to have a global access, for them it's good. But if you don't have the kind of a global access and doing it, so we say that it's fine. People are trying to put our own things, and at the same time, there are some security concerns as well, right? So, and based on the security concerns doing it, we say that, no, the public clouds are not good enough for putting everything onto the public, right? So then you need to have your own mechanisms being maintained, right? So you need to go for the kind of private cloud or community cloud which is set up, and use these frameworks like HPC frameworks, what the industry does, and set it up and use them. That's where I wanted to tell that HPC, where as an organizations comes into the existence to build the kind of frameworks and do that, right? Okay, now let's move on to the being understood about HPC technologies and blah blah blah, right? So much of things that we understood. Now, one of the thing which comes as an HPC now, where we are getting into the AML, right? So AML, as everybody understand, AML, A and ML or DL, which has become like a very very popular, right? People whosoever we touch, I'm sure if you're from academic institutions, if you've been like a faculty is working, and if you touch anybody, hopefully I'm say that, no, 9 into 10, 9 is to 10. That means even if you touch every 10 people, you will see 9 people working on the A and ML, right? So I'm damn sure even it could be, the percentage could be 100, right? It's not 90%. Sometimes it's more than 90%. Everybody talks about AML, and whoever you touch, they say that, sir, I am working in AML. And we say about what kind of an AML. So somebody will say that, no, AML, I'm working for the agricultural. Somebody say that I'm working for precision agriculture. Somebody say that I'm trying to work for the sentiment analysis. Somebody say that I'm working for the object detection. Somebody will say that, no, I'm working for, no. So blah 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 blah. So many things will come for the A and ML, right? So, but whoever you touch, people ask for the AML, right? People work for the sentiment analysis, like a different types of problems. People will like a multimodal analysis, and somebody will work on the speech, somebody will work on the audio, somebody will work on the video, somebody will work on the image, right? So, but people trying to address this A and ML problem, even the speech processing, and people also try to use the speech processing also for the sentiment analysis, no, keeping into the thing and do this lot of works which has been done. It's good. I'm not saying it's not bad. It's good, because the various opportunities of this field has given to the various people to select a new field and work it onto that, right? Like for example, if we talk about a cloud, edge, fog, and these things have become like, the back end technologies for many applications to realize. Now the applications, it's a time for us to realize the applications. So that's what I'm saying. A and ML is basically given a birth for realization of an applications. I say that A and ML is in fact has given a birth for the last mile connectivity, right? We always use the word called last mile connectivity. So that when you talk about a last mile connectivity, that means you are trying to address the real problems where it is meant for the community to be given, right? So the community or the user community, or it could be the society where you wanted to give. And AML is an applications which has given most of the things which has been done, or even it could be the autonomous navigation systems, or it could be the driver assistance systems which we like an ADAS, right? Or we call it like, no, the driverless cars, right? So which people are trying, which the companies are trying to address, and coming like a different types of phases, starting from, type 6 to the type 0 to type 6. They call it a level 0 to level 6, where level, in fact level 5, where it's called like a fully autonomous vehicles, right? So there is no driver. It's a driverless vehicle. When you call like a fully autonomous, the vehicle, right? And also it has also given a birth for many other vehicles, which is like unmanned aerial vehicles, UAVs, which are also a drone. Now you see that wherever drone, people are trying to talk about for UAVs and drones, like, no, the very popularly emerging, right? So like many states are also now focusing on the drones, where they wanted to use these drones, and especially for many of the applications, starting from agricultural field, even to the navigation, even to the no, mapping, even to the surveying, and even for communication, and even to the packaging and delivery also, right? So that means all these things, how they become, because the systems has become more robust, and systems has become like more of giving an intelligence to them, and most of these AI applications are running on the systems, right? So that means they've been the applications, now they want to have the more computing power, and this more computing power has to come from the devices, and these devices of edge computing devices are coming with GPU, FPGA, CPU together, and you can able to put like a sensors, like an IoT sensors, collect the data, process the data on the edge itself, which is closer to the source, and finally the decision you want to transmit, you transmit the decision to the first system will take a decisions on its own, and finally if you want to transmit the output to the ground, you transmit output to the ground, this decision has been made, right? So that's where these systems are becoming very popular. Like for example, if you talk about a drone, so drones are now used for many applications, right? So like one of the applications talk about for the spraying applications, where you could able to put a control, it will spray and come with very fast rate. You can also put it like surveillance and mapping applications, where it will fly, put a camera, takes and do that. Or you wanted to search for an object where it's been happened, you put your deep learning algorithms onto the edge computing devices, where it is running on the kind of NVIDIA systems like a Jetson kind of a boards, where it runs and gives the results back to that. And also you wanted to build an obstacle avoidance system and put it and run this obstacle avoidance system. Or I wanted to do the kind of the object detections. Let's say for example, I wanted to do the tracking of a car, or I wanted to count the number of vehicles, or I wanted to find out, see that with very track the person and find out, or I wanted to see that how much of the people are around, right? Or I wanted to find out even for doing this kind of a mapping of an applications, where I wanted to enter mapping of a city, right? So like this, there's so many applications people are trying to do this, right? So that's where these systems are becoming very popular. And for all of them, obviously the AI and ML and the deep learning becomes like more of the interesting subject, right? So AI, as everybody knows, artificial intelligence is the big umbrella, where the technologies like machine learning and deep learning are encompassed as a part of an AI techniques, right? So again, machine learning more of statistical approach, where the data works most of the statistical way, where it could be like the algorithms, which is like a support vector machines, it could be the random forest or the decision trees, right? So all these things are even to the other logistic regressions, right? Or maybe the regressions, all these things will go like machine learning techniques, where the data is fed to the things, and the data is modeled, and the model is generated, and after that you give it data and do that and get an output of it. So that's where the machine learning will go into the things, right? So but obviously to run the machine learning techniques, you need a computing power. So there is an HPC technology which is going to give the computing power. This is an obvious, right? HPC becomes as a backend computing technologies. Now coming to the deep learning. So the deep learning is, as I told, it's like a neural network based, right? We call it neural network based, and that's where most of the application, when you talk about a neural network based, so one of the popular is the convolutional neural network, CNN technologies, where the data is given and the model is created by the neural network architecture, and that becomes like your network, and the data and weights parameters are generated, and these weight parameters are loaded again for you whenever you get a new data, right? So that's what, like for example, if you talk about the object detection, right? Object detection or classification. So I take the data and I wanted to first create the label data, and the label data is given to the network, and the network is trained, and you get a model parameters, and take those model parameters weights, and again whenever you get a new data, give it to this model weights, and it will go to that architecture of the network, and finally what you get is that once it goes, finally what you your the result, and these results once you see, you'll get like a classification parameters. Depending on the classification, you could able to see the percentage of level of a classification, then you can do it. In between there is many other parameters which comes like an accuracy, precisions, all those things will come, but we are not getting into that, right? But whenever you try to do these kind of systems, either it could be like machine learning, deep learning, and for that you need the computing infrastructure, right? So this computing infrastructure is in fact, for all of them, is driven by the HPC kind of a facilities to do that, right? So these are all the different types of the the boards, or I can say that the computing power, where this is a GPU you talk about, this is like a Tesla card which is from NVIDIA, where it has the so much of computing power, and this is good for performing the computation for the data parallel kind of an applications, right? So like you can see, each becomes like an accelerator, where it goes and sit onto the CPU as a CPU PCI bus, right? It could be like the different types of generations are available, like a PCI slot, and it becomes like a co-processor, and whenever there is a computation of the job has to be done, CPU directs the to the GPU to do the computations, right? So the buffering has been taken care, and the data from CPU is copied to the RAM to the GPU memory, and the applications executions happens on the GPU memory. And once the execution happens, again the results are pushed back to the CPU. From the CPU, again you can take the data back to that, right? That's how the GPU comes into the things, right? And yeah, this is the HPC for deep learning, where we can have the layers which I was talking about for the neural network based architectures, where we have the input which is given, right? And so network is trained by the input data. Then after that you can have the classification of the last input data, which goes like a first, and you can have the in between so much of hidden layers, fully connected layers, and where this data gets trained. And during a training, it goes into many steps, like we have a steps like a training, validation, and testing. And based on that, the biases are adjusted. As the biases are adjusted, your network becomes like a more of stronger, strengther. Then the accuracy, the will get improved, right? It could be an accuracy and precision, or it could be the medium map and many other parameters which come. So I'm not trying to teach completely the deep learning, but this is how it happens, right? So but whenever you try to do the model, once it generated, network when it is trained, model get generated, then finally the model can be used again for the inference, right? So that means inference is what you're trying to give and get an output of the given the data, right? For example, if let's say if this network I'm trying to use it for the classification, so what I'm getting is a y not to yn is the number of classes, right? Like for example, you have an image, and the image I have a different types of objects, let's say. Okay, the object can be, if I take an image, you can have a different types of objects, right? It could be like you may have a laptop, you may have a table, you may have a the cup, which is like a cup which is being kept for a tea, coffee, right? So like you can have even the pen. Like these are all, each one becomes like a class, right? So these classes can be trained, and these training data sets are being fed to the network. And the network, you can take like which kind of a network, right? So you can have a VGG, you can have a ResNet, different types of things that you're going for classification, or you want to go for a detection. You can also have a different types of YOLO models, right? So those networks will get trained. Then after that, finally you have the model which is created, and this model can be used for further doing the kind of inference, right? So these are all the steps. But at each phase, if you see, the computing is must, right? So that means even to train this network, you can just imagine for the training, people spend, especially for training, a lot of computing power is required, and especially for the large language models like in LLMs, you need a very very lot computing power, right? Like people talk about the chat GPT, right? GPT are already, even directly or indirectly, everybody may be using the chat GPT, right? Based on the transformer models, no, generative pre-trained transformer models, which also like a generative AI. So when you talk about the generative AI kind of an applications where the models like Llama 2 or any other framework which you wanted to do, open source based the LLM models, you need a lot of computing power to train your network itself, right? The data sets you require, on the data sets you'll be training it, and you need a lot of computing power to do that, right? So that's where the HPC frameworks comes, and doing and giving a lot of power to do that, right? So that's how you need to see the HPC where you can able to do that. Now coming to the edge HPC computing. Okay, HPC means as I told you in the beginning, don't think like it's always goes like a server based computing. Now the HPC also moved to the edge, right? That's a beauty of HPC now. So that's what, even if you talk about for HPC edge, HPC edge computing itself, you can talk for hours, right? Like the way you talk it for servers, you can talk it for HPC edge for many hours, right? So there's so many HPC devices are available, starting from the Jetson models itself. The Jetson NVDI also has the many models, starting from Jetson, the nano boards, Jetson TK board, Jetson TX board, then the Jetson nano board, then after the Jetson Xavier board. Again, Xavier has the many models of it. Again, the Jetson Orin board. Again, the Jetson also has giving the something called the cluster based edge computing, which is called Jetson Mate, right? That goes more of depth into, again, taking to another scenario. So you can search it for the edge cluster computing, where all these edge devices are divided, again joined like a cluster based computing, where edge you can perform the cluster computing on the edge itself. That becomes edge cluster computing, right? That's another topic itself that goes for again hours to speak about. Now there are so many edge devices are available, right? So where they have become like very popular, and some of these commercial available edge devices, when you talk about like Echo Dot or Google Assistant or Amazon Alexa or Siri, there all becomes like most of like edge kind of devices, right? So when you talk about the HPC cloud and edge for DL, there's a lot of applications which have been there, right? So this which have been done, especially which the like applications of a drone which have been used for the military and emergency purposes. It's also used for the disaster management, where the edge device of HPC edge device sits onto the UAV vehicle itself, where you could able to perform and do that, right? So that's where the different applications like a scientific research, security, agricultural, and so many things which have been done, right? So this I don't want to get into some of the things. This is what I was talking about, edge computing device, where this becomes like a Jetson board, which is called the Jetson Nano board. And you also might have heard about a Raspberry Pi, right? Raspberry Pi In fact, is an edge device, but it's not an HPC edge device. It has a small computing power. But HPC edge, when you talk about, you need to have the large computing power which can able to perform. So NVIDIA comes with HPC kind of edge computing devices, right? Okay, that's where which comes into the doing into that. Okay, now as the time is, many other slides are there. What I mean to say that I'll quickly introduce you about the another new era of HPC computing, which is the cloud computing. Another HPC era of moving from the cloud. Now we talk about cloud, edge, fog, other kind of IoT, and also the the supercomputing that we talk about. Now we'll move into the new era of the HPC computing, which we call like a quantum computing, right? So that's a new HPC era, and obviously this is very very new topic. I thought let me give a small introduction of the quantum HPC computing, so that it will be an interesting for the people and those who wanted to do the research, right? You can able to pick up this quantum computing as a new research area, and now you'll find a lot of opportunities and problem statement to work on the quantum computing as a new HPC era, right? We already guided some of the students who are already done PhD in the quantum computing, especially quantum for HPC and AI. So some of those things will goes into a late of again another topic as such. So we thought of introducing the quantum computing and give you the quantum computing, how it is driving a new HPC era. Okay, so let's see that quantum computing is the use of, as we told, it's not a classical computing, right? In the case of classical computing, we talk about a bit like always 0 or 1, right? So when you talk about a bit, so bit is the smallest unit of representation of a memory, and this bit represent either 0 or 1, is a deterministic, right? You cannot have existing both together. That means you cannot say that it's a both 0 and 1, right? That's where it comes like classical computing. But when you talk about a quantum computing, what we say that the bit, when you talk about, the bit can be either 0 or 1, or any state between 0 or 1. That's where the beauty of the quantum. That means, let's say that in the case of, just take a single bit, in the case of a single classical bit, you can say that either 0 or 1. But in the case of a quantum, when you talk about, it's a one bit represent two states. It is not a single state. Like in the case of a classical, when you have something called 8-bit register, right? So that means one byte. So at any point of time, when you talk about, the state can be only one state. So that means it could be like a 0 1 0 1 0 1 0 1, something like this, which goes like a 8 bits. There is only one state at any point of time. That means when you talk about a register, the register can hold only one value at any point of time. But in the case of quantum computing, when you talk about, it is not the one value. The register of 8-bit register will hold the number of values. You can vary the 2 power of 8 values. That means 2 power of 8 equal to 256 states, right? So earlier case of thing where it holds like one state, but in this case now it can hold 256 states. That's the beauty of the quantum, right? That's where the quantum computer has become like very popular, especially for breaking many of the classical systems where the securities are becoming like more of vulnerable, right? Like for example, if we talk about AES, GS, or even many of these computational problems where the classical computers is unable to address the security, is classical computer is unable to break the most of these security related algorithms, and those things are being now looked into as a quantum computer as an alternative solution where to break up all these algorithms, right? So that's what people are talking about post quantum immune now, right? Like a PQC, post quantum cryptography, right? So that's where the quantum computing become more of popular. That's where the things like when you talk about like a 10, in the case of a quantum, we call like we don't call like a bit, we call like a qubit. That's QUBIT, right? So QUBIT, the qubit is not a classical bit, it's a quantum bit. That means if you have a 10 qubit computer, you could able to perform 2 power of 10 computations together, and if you have a 30 qubit, you can able to perform 2 power of 30 computations. That means whatever the exponential problem that we are talking about, where you cannot able to solve like a 2 power of n problems, these 2 power of n problems can be addressed with the quantum computing much better way. That's the beauty of the quantum computer. That's what we call like HPC now is moving to the quantum computers as a quantum HPC computers, where a lot of computing power has been driven using these the HPC world. Now there is it's not quantum is maybe in the reality, though it is going to take some time, people are thinking about, but is going to come very soon, right? So even the India also has the Prime Minister has launched the quantum computing machine, where a lot of funding has been given and a lot of research has been going from the many of the academic institutions. Not only that, even the industry is also focusing on coming to the kind of quantum computing as the technology we're bringing, and it will sit as the way we talk about the accelerator computing like a GPU, FPGA, and quantum processor, which is going to sit like a quantum co-processor, right? If you want to have the deterministic computation to be done, the quantum processor will sit adjacent to the CPU, and obviously the deterministic problems, especially the probabilistic problems to be solved, they'll be given to the accelerator of a quantum. It's going to come very soon, right? That's going to be, get ready for them, right? So, and as a computer science, get ready to design the algorithms also for a quantum, right? So you need to write an algorithm where the quantum computer can able to solve, like the way the block processing using the GPU, streaming application like an FPGA, and using a probabilistic model in the quantum computer, right? That's where the beauty of the quantum, and the quantum frameworks, quantum programming languages also come, and there are many frameworks which is also coming. Like for example, if you talk about the IBM already released the IBM already released this framework which is called as they call like IBM IBM Q, IBM Quantum Computer, where they call like a Qiskit, QISKIT, right? So this is the Qiskit where IBM has already released as a software development kit where you could able to design the gates and do that, right? This is called the Qiskit. Similarly, Google also has come up with something like a TensorFlow Quantum, where it is meant for the quantum machine learning applications, where you could able to use the simulators and doing it. Like there is one more library called the Silk. This also can be, you can able to design the models, right? So I think my presentation for quantum goes for again for many hours. So I thought of just introducing you, and there are many applications where the quantum applications being used. One is the cryptography, and if you talk about the quantum and the classical bit, in the case of a classical, the bit is either 0 or 1, right? So like what you see here. But in the case of a quantum, it is not 0 or 1. We call it like the probability between any value between 0 or 1, right? That's what we represent. If we talk about this, we call like not a bit, we call this like a the ket, right? Like a ket 0, ket 1. So in the case of quantum, we won't call like the 0, we call like a ket 0, ket 1 here, right? So like ket, if you see here the bracket generally we have it two things, right? But this is an half of a bracket, that's why you call it ket. Remove from the bracket the BRA, if you remove the word, it becomes like a ket. It's also ket 0, ket 1, and a plus and divided by root 2, and this is what we call like a block sphere, where the quantum bit is getting represented. Based on that, the measurement is made. So mostly this is based on the measurement kind of a techniques to do that, right? In the case of a classical bit, either whole size 0 or 1, but in the case of a quantum, you can have the any state between the 0 and 1, and this word representation happens, right? Like for example, if you want to get any value, so it puts it onto the block sphere and rotate it, then you get the data, and this data can be experimented with the cause and the sign, then you'll get a value for doing it, right? And one of the beauty of this quantum is, as a supercomputing, if you want to achieve, you need to have the gates, like the way we define the classical gates, like OR gate, NOT gate, NAND gate, XOR gate, right? The different types of gates. Here also we have a gate, quantum gate, right? So we call like a Hadamard gate, which is meant for the the things for the Pauli XYZ, then the phase and the pi by 8, right? These are different gates one has to decide, and these gates comes from the thing. You can read my paper, which is on the quantum machine learning. I hope I have the last slide. Maybe I might have kept it. You can go and search my name with this with the name, where you can assign, say that quantum machine learning. You will see most of the papers coming appearing from my side. Quantum machine learning or hybrid classical computing, where you can go and search in the Google. And they're all made like open public now for the people to refer them, right? So where you will understand about how this quantum machine learning has been coming into the thing, and how the research has been going in the quantum machine learning. You can search quantum machine learning in the Google. You'll get my paper as the first paper. Now, the quantum machine learning is an emerging field in the computer science with the quantum computing and machine learning. That means if you see most of the machine learning problems, they're all like a probabilistic in nature, right? So probability based. As quantum computing is better for the probabilistic model, so can we link this quantum with the machine learning so that the results are much faster and much accurate? That's the beauty of quantum linking with the machine learning. That's where my papers talks about, right? And when you talk about a quantum computing programming models as a framework, there are many frameworks are also available. One is called the SIG, which is a Python library for designing the circuits. Then the TensorFlow Quantum, where you could able to design the circuits. And Qiskit is the programming model where the SDKs are available where you can run. And there is another, the quantum machine learning based problem which is coming from the Google, which is called as the penny lane, right? You can be able to design the circuits and give it to for the machine learning to do that, right? So these are all some of these my publications where we talked about the training on artificial neural networks, a quantum computing approach, and there is another papers which talks about and doing it, right? So that means if we talk about the HPC technologies, as I told, it is now moved. HPC has moved from the server computing to the edge. Now the HPC edge has become very popular, and after that, there is a lot of computing power going on to the HPC edge. And from HPC edge, there is a lot of artificial intelligence and machine learning techniques have been running for most of the navigation systems. And after that, lot of inferences models are getting executed on them, and there's a lot of results which have been taken, and decision also has been made, which is becoming like very popular in doing it, right? So let me introduce about how these the HPC edge things are going for doing it, right? Like for example, if we talk about the HPC on the edge computing side, HPC frameworks and doing it, how this been done. If you see that there is a swarm of drones which have been not doing. If you see that they each one like working like a bird, right? It's not a bird. In fact, that's a drone. You could also see nowadays the drones which have been used for most of these, the applications like entertainment applications, like a swarm, right? They call like a swarm, where there is a drone shows are also conducted, right? You could have seen now drone shows. The shows have been conducted with the drone. They make different patterns, right? So when you say that all of them work like a swarm, talking to each other and sharing the information to do that, right? And but how do they share? They need a power, right? So there is a computing power put it onto these vehicles. And how this computing power is coming? The computing power is coming from the edge based devices, because edge runs at the source, wherever the data is generated. Now there is a computing power which is given, and lot of data has to be processed. So there's an HPC edge where it can able to process and give the decision, and the decision, once it is taken and it is passed on to the next device or the next drone which is working, that's where the HPC edge does. Like for example, if we talk about this boat swarm in action, and you see this person is in fact trying, and is trying to watch any collision is happening. And if you see on this pattern, each one is a robot, is like the surface vehicle. And these one runs, and there is a obstacle here, and wherever there is an obstacle is coming up, you see that they have taken a path such that they will not collide, right? And they went and they avoided this path, and they went, right? So that's the beauty of when you try to put this kind of the edge-based computing devices, giving intelligence to that. These are all autonomous vehicles where a lot of research has been going on, where the intelligence is being given. So you can see that there is a persons are moving, and there is the vehicles are moving, and there's different types of vehicles, right? So the autonomous vehicle has to take a decision. It is in fact is waiting for someone, right? It will not move until this line is being cleared, right? So and a lot of industries and things are working onto this kind of an autonomous vehicle. So this is one of the thing where you can watch these technologies of a drone light shows. And recently, even at Amaravati also there is a drone show which is conducted, which is being given as a based on the AI kind of techniques, right? So these are all the different things which I wanted to tell, and these different devices where the cloud and edge based kind of a computation which have been happened as an HPC models and doing it, right? So I think time will take a lot of things. And also there are all the different types of edge computing devices, and also see that even these edge computing devices are not only used for the image processing, they're also used for the signal processing, right? That means especially those who wanted to work on the radio frequency based things, like the technologies where you wanted to see how these kind of radio frequency devices have been operating, especially for the GPS spoofing and the kind of things. Also the deep learning mechanisms have been working, right? There are many things which has to be like, these are all the voice based mechanisms where you can able to do and detect and do that kind of things. Okay, right? I hope any questions I leave for some the platform for the questions to take out, if any.
Yeah, there are few questions, sir.
Let's take up.
After the feedback, there is a question: what is the impact of deep learning on HPC? Is one question.
Okay.
And then can I read out 3-4 questions if there are any common?
You can come one after the other so that I can give an answers to them.
Yeah. What is the impact of deep learning on HPC? It's one question by Professor Subbarao.
Okay. What is the can you repeat again? Let me understand
what is
the question.
impact? What is the impact of deep learning on HPC?
Okay, so if you see the impact of deep learning on HPC, yes. So the impact is goes like this. There are two folds it goes. The first fold is for the training of your network. That's one impact. So for the training of a network, of training of your network and generating a model with the model weight files, obviously there's an HPC platforms are required, right? So that's what when you talk about for the most of these machine learning and deep learning, because you are talking about deep learning, let's focus on more on the deep learning. So the deep learning applications, they need a lot of GPU computing power. So the HPC based GPU clusters have been established, and for the deep learning, if you wanted to get a model, your network trained, and your data will be pumped to that, and there is a there is a lot of computing power is being taken from the GPU clusters, and the HPC GPU clusters plays a major role, especially for the training of your networks, right? Training on the network, on the data. And especially, I tell you one more thing is, those who are working on the generative AI, the HPC impact is more for the deep learning, right? So the deep learning, if you want to do for the generative AI kind of an applications, like especially the transformer kind of a models, where I have a large data, where I wanted to make the model, either it could be like a fine tuning, or it could be like a retraining, or it could be like incremental training we wanted to do. Obviously there's an HPC platform is required. And setting up HPC platform on the own by someone, putting that kind of infrastructure and investment is also very huge, right? So they're very huge. And that too, nobody tries to know, as a it could be like any company, for their purpose, or even for the individual, or even for the research institutions, putting up that kind of a platform for HPC, especially for no, doing the kind of the training of the LLMs, like a generative kind of a models, is very very expensive. So they depend on the HPC platforms from the cloud. So now HPC platform, when you talk about for a cloud, Amazon or even many other cloud based services are giving these HPC based GPU clusters or GPC computing for AI HPC based systems as a backend systems to do that, right? So that's where the HPC power comes onto the deep learning applications, right? And other is for the same deep learning, the second fold which I talk about, this is for the inference applications, right? For deep learning, one is for the platform which goes for the training, put it onto the HPC platform, like the computing platform, which is like a very large computing system. And when you wanted to do the inference also needs the HPC, especially on more of the edge GPU power, right? So then there's a smaller platforms runs as an HPC edge device where the inference can be done. And this inference, when you want to do put a model on the device, like a Jetson board, which I was giving an example of this, then put your model, then whenever you get your data, do the inference. So inference needs the HPC platform as an edge. Obviously, second one is the for training, validation, and incremental learning, or retraining, or pre-training for those kind of models. You need a HPC platform as the backend computing facility for large, right? So this how two things becomes as a impact for the deep learning as an HPC platforms.
Yeah,
Okay, I hope I answered. Yeah.
yeah, yes, sir. Thank you, sir. And there is a one help is seek by one Professor Pratha Tambe. How to use or install MATLAB on HPC? Can we schedule a session for the same? And please guide if any video is available for the same, as I'm unable to do it. So the professor is asking how to install MATLAB on HPC architecture. I mean environment.
Okay.
Is
So
there any
maybe the
reference?
professor can contact me later. We can share my Gmail ID to madam so that I can help her
Sure,
no, to do the
sure,
part.
sure,
And
sir.
I
Just
hope
follow
she is looking for the kind of specific
help. Correct.
applications purposes, right? So it's not like a MATLAB installing an HPC. It's a basically development of a MATLAB based applications which can run on the HPC platform. So I'll reframe the question like this.
Yep,
Okay.
yep.
With MATLAB kind of
So
an applications where I want to run an HPC platform, you need to have a MATLAB runtime environment, and this runtime environment installed onto the different types of cluster of nodes, and put your application such that it runs into the parallel systems using the same .m file that you're talking about. So okay, so that's a question I'll reframe in that fashion.
the next
Yeah.
question is, yeah, you have addressed it, sir. And the next question is the quantum computing used in deep learning models. Of course, you have discussed this. This question come a bit early, but you have covered this
Mm.
quantum computing used in deep learning models. Is the question?
Mm.
Yeah, I think you have addressed it in your
Yeah.
explanation.
Yes.
Uh,
So this is if you talk about something like neural networks, which is like an artificial neural networks, ANN, we call it a quantum artificial neural networks, right? So these things goes like thing, and also making these neural networks completely quantum becomes somewhat difficult as of now in the market. That's why there's a hybrid approach. In the case of a hybrid approach, we try to introduce both the network which is coming from the classical networks and the quantum network. Both joined together becomes a hybrid approach where you could able to train the network much faster way, and also more of better accuracies can be achieved. So that becomes like a quantum artificial neural networks having an approach of the classical and the quantum. Okay, please read my papers. I think most of the things get cleared.
Yes, sir, one follow-up question is uh, how optimizers are used in HPC? So it's a little interesting question. And as we
Yeah,
talk about a lot of parallelism,
correct. So the optimizers used is, it has to come from the programming side, right? So like for example, one of the example which I'll take up again for the optimizer is, let's say that when you are trying to make any HPC applications, first thing which we need to keep in mind is whether your algorithm can be parallelly made is first thing we need to do. So one is the optimization is how can I make my algorithm into more parallel. So that's the first optimization. So when you're trying to make this algorithm as the first optimizer as a parallel, now for each parallelization you also need to see that how much of that memory that I can able to give, right? So when that's the second optimizers. One is the parallelization, which is on the number of threads that you could able to create, or the number of processes that you can create. That's one optimizer. The second optimizer that you talk about is on the memory side, right? So you need to also make use of the memory effectively as much as the minimum as possible. So that means if I wanted to the declare, or if I wanted to assign any memory to that, I need to see that only the optimal memory can be assigned for the particular process or thread. That's the second one which we need to do. Then the third one is, if I'm trying to execute and if I have a problem where I'm trying to combine the multiple threads into the thing, I need to make my thing such that I could able to combine them without having much waiting time, right? Don't try to see that wherever you have some kind of the more number of loops, per loops, those kind of links, wherever it is not required, try to avoid them. So that's what one of the thing when you talk about HPC programming, we first say that avoid the wherever there is a more number of computational cycles are involved. So don't put like a for loop. I think probably those who are coming from the bubble sort, if you try to see, bubble sort is very too easy to write, right? Because with the for loops you could able to do, with the the two for loops you could able to do. But the same thing if you go for the heap sort, or if you try to go for the other kind of a mechanisms of a sorting, the quick sort, the logic is improved, right? Heap sort, when you go, the logic you have to write lot, because in the heap sort you don't find the for loops, right? You'll find like most of the conditional based things, right? So try to remove wherever there is a more number of statements are involved. That's where you have to do. And the next one which is more important is try to write the scheduling approaches, right? So try to put like the schedulers where you could able to compute the load, get the resource computations available on the load, and based on the load computations try to schedule the things, right? So one is first to try to focus more, one optimizers which we need to see is focus more on the algorithm side, looking at number of threads, number of cores that you required, minimize it, see that it is not more of computational intensive, try to reduce wherever there is a for loops are there. So try to go for a conditional kind of a statements rather than more for loops kind of a things. Then try to minimize the memory, optimize the memory where it is required. Don't declare, don't assign the variables or memory as you want, right? People try to assign the memory they wish they wanted, even if there is a requirement there or not. They try to declare an array, and the array has something like thousands of elements, right? And they never release the memory. That's another problem which comes into the HPC. And the systems goes into the memory leaks, it will shut down, entire applications get shut down, right? That's another optimization which you need to do. One is the parallelization for the cores, second is the memory, next is the computation, remove the things wherever there is a for loops are there. Then the next one is try to see that how much of a load is there on the system. So try to use the load balancing mechanisms, and when you use these kind of a load balancing mechanisms, obviously what you get a performance will increase the better, right? So one is the threads, other is the memory, try to reduce the computation cycles if at all loops if you're trying to use, and other one is try to use the load balancing mechanism so that your applications gets executed on the system where there is a load is less on the system. So that's another optimizer which you need to think. There could be other optimizers are available, but these four things are which you have to see critically when you're trying to make an HPC application.
Yeah, yes, sir. Thank you. And probably this is the last question. If quantum computers become widely available, what role will high performance computing play in computational science and problem solving?
Yeah, so the high performance computing remains same. For the deterministic problems, yeah, classical HPC will work, and for the probabilistic models, obviously quantum HPC will play a major role. Right. So is now you will see later point of time. Maybe if I have to give a talk,
Yes, sir. Yes,
maybe
sir.
after
This is
few
the
years. So obviously I need to divide my talk into two parts. One is the HPC classical, other one is HPC quantum. Okay, hope so.
any,
Very soon it may happen.
sir. Anyhow, we are going to plan one more FDP on quantum computing soon. So we
Yeah.
need your support, and then definitely
Yeah,
we'll
definitely.
extensively discuss
Yeah,
about quantum
theoretical, but
computing.
I'm also
Yes.
talking about on the practical side to explain for the quantum HPC practical to explain. So maybe I'm hoping for another few years where things will get evolved. For me to wet my hands. Okay.
Thank you, sir. Thank you,
Yeah.
sir. Yeah. If there are no questions, let me take opportunity to offer the closing remarks. It's my privilege to offer the end remarks for this highly knowledgeable and then enlightening session on particularly artificial intelligence, machine learning, deep learning with high performance computing and its frameworks. And you also touch upon the edge computing, quantum computing, and on behalf of the entire Chaitanya Bharati Institute of Technology and the Department of Information Technology, on behalf of the coordinators and the participants, I really thank uh, Dr. Raghavendra Kune for your outstanding session. Sir, really, your deep knowledge that what you shared with us is no open. It's an eye opener for us to think next level, because now everybody is talking about the high performance computing and the quantum computing, edge computing, and particularly even you spoke about the aerial artificial intelligence. So these are the areas where the computer science is really focusing on to optimize the applications and better use the resources. Today's session, no doubt, is an eye opener, especially in the form of understanding particularly the basic concepts and the directions towards developing applications and how they are really used in industries and research and innovations in critical areas like what you shared in healthcare and the real world examples, like you also focused on certain applications in aerial applications like drone applications. So uh, these made us to think more advanced technologies in addressing the most of the challenges. This session has not only broadened our technical knowledge but also motivated us to take up the new research directions and opportunities for collaborations. Thank you very much, sir, for your wonderful session. Finally, thank the participants, because you see, sir, both in YouTube and then here put together, there are 210 participants are actively listening the session. So this shows the how important the session and then how you engaged it. Once again, I thank you very much for sharing your expertise and speaking and making us listen curiously on this session, sir. We look forward uh, for the more future sessions with a great anticipation. So thank you once again for your wonderful session, sir.
Thank
But
you.
I'll also share with you the feedback.
Yeah, please share the feedback. It will help me a lot to improve the content, especially on the moving from the classical computing.
Yes, sir. Yes, sir.
HPC
Yes, sir.
classical, right? Not moving,
Yes, sir.
augmenting the HPC classical computing, I say, right?
Yes, sir. Yes, sir.
Okay,
Yes, sir.
right. Thank you. Thanks a
So
lot. Thanks a
Thank
lot
you,
for
thank
the
you.
Raghavendra sir.
opportunity. Yeah, thanks a lot for the
Thank you,
opportunity,
sir.
and all the best. And thanks for joining. Thank you.
Thank you, sir.
Yeah. Good night, sir.
Good
Good
night.
night. So, dear participants, we have shared feedback link in the chat box. I request all the participants to provide your feedback by the end of the day. Muti sir, is anything to announce?
Done from my end. I done from my end, sir. I forwarded all the feedbacks in the. Thank
Yeah,
you.
please, I request everyone to please fill your feedback by the end
Yeah.
of the day, because the sessions will be closed. I mean, the sessions will be closed and then forms also will be restricted on the same day.
Thank you, sir. Thank you, sir. Great day, sir. Good night, sir.